This video is for Physics of the Universe, Unit 1.3, using vectors and scalars to describe motion. Today's essential question is, how many problems involving two-dimensional vectors and their components can be solved? And what are the effects of forces on an object's speed and direction? Hello, baby birds. Today we're diving into one of the most important concepts in physics, vectors in two dimensions. Our main phenomenon is something simple but powerful, running a race. When you're in a race, you're not just moving, you're moving with a specific speed and in a particular direction. And that's the essence of a vector. In this video, we'll learn how vectors work, how to add and break them down, and how they influence motion. Mastering vectors helps us understand everything from sprinting to spaceship trajectories. To begin, we need to understand what a vector is. A vector is a quantity that has both magnitude, how much, and direction, meaning which way. This is different from a scalar, which only has magnitude. Think of temperature. It's 30 degrees, but it doesn't point anywhere. Now think of velocity, say 10 meters per second north. That's a vector because it includes direction. We draw vectors as arrows. The length of the arrow represents the magnitude, and the arrow points in the direction of the vector. For example, if one runner is going 10 meters per second and another 20 meters per second in the same direction, the faster runner's vector is twice as long, meaning the arrow is twice as long. Point in the same direction, we can add them easily using the head-to-tail method. Imagine one runner pushes a sled with 10 newtons of force, and a second runner joins in, pushing with another 10 newtons in the same direction. We can place one arrow with its tail at the start, then place the second arrow's tail at the head of the first. The resulting error, meaning from the tail of the first arrow to the tip of the second arrow, is the resultant vector. It shows the total force, which in this case is 10 newtons plus 10 newtons, which is equal, calculator ready, 20 newtons in the same direction. But what if the vectors are in the opposite direction? We still use the same idea, head to tail. But now, in this case, we subtract the magnitudes. So suppose a runner pulls a rope with 20 newtons to the right, and another pulls 5 newtons to the left. The forces oppose each other. So, in this case, we subtract 20 newtons minus 5 newtons, which is equal to 15 newtons. The direction of the resultant vector is toward the stronger force, in this case, to the right. So the final force is 15 newtons to the right. Now, when vectors are at an angle, we use the parallelogram method. So imagine two runners pushing a sled at different angles, not straight ahead or directly against each other. From a common origin, draw the two vectors as adjacent sides. Then complete the parallelogram. The diagonal from the origin to the opposite corner is the resultant vector. If the vectors are perpendicular, we can simplify this using the Pythagorean theorem. High math class. A squared plus b squared is equal to c squared. This is useful in right angle cases, like one runner pushing north while another runner pushing east. But what happens when you have more than two vectors? Maybe you sprint forward, turn right, then veer diagonally. You add vectors using the head-to-tail method. Start with the first vector, then place the tail of the second at the head of the first, right? Head to tail, and so on. After placing all the vectors, draw a single arrow from the tail of the first vector to the head of the last vector. That is your resultant. The order doesn't matter. You'll get the same result. This is how GPS systems calculate the shortest path from multiple steps. Any vector can be broken into parts, but we call these parts components, component vectors. Think of a runner pushing at an angle. That diagonal force is really made up of two simpler forces, meaning one horizontal and one vertical. These are the components of that vector. So breaking vectors into components helps solve complex problems much more easily. For example, it's much easier to add horizontal forces to horizontal forces and then vertical ones to vertical ones. We usually resolve vectors into rectangular components, meaning we've aligned with the x-axis, which is the horizontal, and the y-axis, which is the vertical. Why do we do this? Because they're perpendicular, which makes the calculations simpler. So to do this, draw a right triangle where the vector is the hypotenuse. Then you work with each component separately, just like solving a triangle in geometry class. This method is essential for analyzing forces like inclined plane problems or projectile motions. Spoiler alert, we'll be doing those soon. Now comes the math. To find the components, we use trigonometry, specifically SOHCAHTOA. For a vector with magnitude m and angle theta from the horizontal, we know a few things. A horizontal or adjacent side is equal to m multiplied by the cosine of theta. The vertical side, which is the opposite side, is equal to m times the sine of theta. This triangle or trigonometry approach lets us split the vector into two simpler vectors. These components are easier to work with because they act along the x and y axes. Now, while sine and cosine are the most common and convenient ways to find vector components, there are other valid approaches depending on which values you're given. For instance, if you know the magnitude of the vector and one component, you can use the Pythagorean theorem, because we know that the vertical side, in this case, is equal to the square root of m squared minus the horizontal side squared. We can solve that way. We can use the tangent, which says that the vertical side is equal to the horizontal side multiplied by the tangent of theta. Or even, the vertical side is equal to m multiplied by the sine of some crazy stuff, arc cosine multiplied by the horizontal divided by m. Crazy stuff. Also, if you know both components and want to find angle theta, you can use the tangent function, which is what I suggest. The tangent of theta is equal to the vertical side divided by the horizontal side. So theta is also equal to the arctangent of the vertical side divided by the horizontal side. For example, theta can be, in this case on the screen here, is equal to the arctangent of 3/4, which comes out to be about 37 degrees. Specifically 36.87, but we'll round up just for this example. These multiple approaches, and yes, there are many, you do not have to use all of them, but there are many. These multiple approaches help verify our work and provide flexibility in problem solving. Now, let's walk through a full example. A runner is pushing a sled with a force of 5 newtons at a 37-degree angle. We need to find out how much of that push goes into the horizontal, in this case we'll call it forward, and vertical, we'll call it upward, directions. Step 1 is to identify the triangle. This is huge. Draw your vector diagrams. Create a triangle. The original 5 Newton force is the hypotenuse. The angle of that hypotenuse to the horizontal is 37 degrees. And we need the 2 legs, the components. And to find those 2 components, we'll use sine and cosine. First, let's calculate the vertical component, the part of the force that is acting upward. This is opposite the angle, so we'll use sine. So that vertical side, the opposite side, is equal to 5 newtons multiplied by the sine of 37 degrees. So the sine of 37 degrees is about 0.6. Multiply that by 5, and we get 3 newtons. This 3 newtons helps reduce the downward force of gravity on the sled. Now let's solve the horizontal component, the part of the force that pushes the sled forward. This is adjacent to the angle, so we will use cosine. So that horizontal side, right, in this case, it's F2, meaning the diagram on the screen. The horizontal side is equal to 5 newtons multiplied by cosine of 37 degrees. Our calculator tells us that cosine of 37 degrees ends up being about 0.8. So 5 multiplied by 0.8 is 4 newtons. So that means 4 newtons directly propelling the sled forward. Together, 3 newtons up and 4 newtons forward are the 2 components of the 5 Newton angled push. Now, what if we didn't know the angle? We can actually work backwards to find the angle using the tangent function. Remember, tangent of theta is equal to the opposite side divided by the adjacent side. So in this case, tangent theta is equal to vertical divided by horizontal. Again, in this case is 3 divided by 4. So, into your calculator, theta is equal to the arc tangent of 3 over 4. For all of my students that do not like fractions, that's the arc tangent of 0.75, which comes out to roughly be 37 degrees. Again, specifically, or more precisely, 36.87, but we'll round to 37 just to make this example a little more straightforward. This confirms our original angle and shows that trigonometry works both ways, meaning we can find components from the angle, or we can find the angle from the components. This flexibility is key in solving vector problems in this physics course. Now, let's look at how the direction of a force affects an object's motion, especially when that object is already moving. Forces can act in a variety of directions, and each direction has a different impact on how the object behaves. Force parallel to motion. Parallel to motion. This kind of force changes the speed of the object, but not its direction, because it's parallel to the motion. For example, if you're running a race and someone gives you a push from behind, you will speed up. You accelerate. But the direction of your velocity stays the same, even though the magnitude, meaning how fast you're going, increases. But what about force opposite to motion? This type of force slows you down. A good example is friction, like wind resistance or dragging your feet while running. The force is still along the same line as your motion, but it's in the opposite direction, which will decrease your velocity. But what about force perpendicular to motion? This kind of force doesn't change your speed, but it changes your direction. A perfect example of this is uniform circular motion, like a runner on a curved track or a satellite orbiting Earth. The object keeps moving at the same speed, but the continuous sideways force bends its path into a circle. So, depending on how a force is applied, meaning whether it's in line with your motion, against your motion, or at a right angle to your motion, it will either change your speed, your direction, or change both. This is why understanding vectors is so crucial. Motion isn't just about how fast you go, it's about how forces and directions interact to shape that motion. Now, let's zoom in on a special case of force and motion: uniform circular motion. This is when an object moves in a circular path at a constant speed, but its direction keeps changing. In physics, if direction changes, it means the object is accelerating, even if its speed stays the same. But why? Because velocity is a vector quantity, which means it includes both speed and direction. So, a changing direction means a changing vector. So, to keep something moving in a circle, there must be a constant force pulling it toward the center of the circle. This force is called the centripetal force, and it always acts perpendicular to the motion. So let's consider real quick some real-world examples. Classic, we have a car turning in a circle. Friction between the tires and the road provides the centripetal force. What about a planet orbiting a star? Gravity pulls that planet toward the star. What about a ball being swung on a string? The tension in the string pulls the ball inward. What about an electron orbiting a nucleus? The electric force keeps it in orbit. Even though the object in these examples doesn't speed up or slow down, it is constantly accelerating toward the center of its path. That is why you feel pulled to the outside when you're turning inside of a car. Your body wants to keep moving forward, but the centripetal force redirects you. Uniform circular motion is a perfect example of how perpendicular forces influence motion, changing direction while keeping speed constant. Now, vectors show up in everyday life. In a pool, you aim, not in a pool, in the game of pool, you aim shots using angle and force, which are both vectors. In rowing, the oar's angled stroke applies force and forward and upward forces, which are vector components again. In the game of tug of war, multiple forces in different directions combine. And of course, in racing, your movement, wind resistance, and applied forces are all vectors. Understanding these vectors means understanding how motion really works. Let's wrap it up. Here's what you need to remember. Vectors have magnitude and direction. We draw them as arrows. You can add or subtract vectors using the head-to-tail or parallelogram methods. Trigonometry helps you break vectors into components using sine and cosine. And forces change motion differently depending on their direction. Parallel forces change speed. Perpendicular forces change direction. And angled forces change both. When you run a race, every stride you take and every push you make involves these physics principles. Understanding vectors makes you a master of motion. At this point, you should be able to generate a full and appropriate response to today's essential question. How may problems involving two-dimensional vectors and their components be solved? And what are the effects of forces on an object's speed and direction?